Hi, I'm Hassan, and in this talk, I'll be discussing two attacks that we show on a real-world tool that's used to query Australian census data. This is joint work with Dalika Farr, and we are both from the Optus Macquarie University Cyber Security Hub. So these are the contents of this talk. I will start with the disclosure control setting, which is the focus of our attack. Then I'll talk about the Australian Bureau of Statistics tool to query Australian census data. Then I'll discuss our attacks on this tool, some experimental results, some mitigation measures, and some inherent limitations if we were to follow the same privacy mechanisms used in that tool, and I'll finally conclude. So the setting that we are focusing on is that of disclosure control. So a data custodian is in charge of some sensitive data from a set of data contributors or individuals, and the custodian would want to have analysts, such as a demographer or a journalist, have access to some statistical insights from this data, but at the same time would like to provide privacy for the individuals or contributors. So Table Builder, which is a tool from the Australian Bureau of Statistics, is a tool to query census data. Australian Bureau of Statistics, abbreviated as ABS, is in charge of managing Australian census data, and this tool lets users create tables, graphs, and maps of Australian census data. The tables are aggregated counts, and the counts are noisy, and the analysts could choose different attributes in the census data, for instance, age and gender, and would get a table of noisy counts. A little bit more about Table Builder. It comes in three flavors: Guest, Basic, and Pro. Guest and Basic are free. Basic requires registration, and Pro is a paid service. And our attacks work on all three. This is a little sneak peek into how the output of Table Builder looks like. So in this particular case, I've chosen a few suburbs in Sydney and a couple of age brackets. And the counts here are dynamically generated by Table Builder, and these are the number of people with the Indigenous status in these suburbs. A crucial thing is down here. As it says, cells in this table have been randomly adjusted to avoid the release of confidential data, and no lines should be placed in small cells. As I shall explain in the following slides, these are at the crux of this Table Builder's privacy mechanism. So crucially, the privacy slash confidentiality provided by Table Builder is to ensure that the output does not lead to re-identification of individuals, etc., from the tables. So to explain the privacy provided by Table Builder, I'll go through a little bit of background. So we could imagine the raw database being arranged as a series of rows. Each row belongs to the data of a contributor or an individual, and in aggregated form, we only see the counts of people belonging to certain attributes in the tabular form. Now, we can't simply release tables, aggregated tables like this, because of privacy concerns. The first one is uniqueness. If the count is high, then the person having those attributes, for instance, age range 30 to 39 and male, could be thought of being provided with some privacy, as the person is hiding behind 34 other people. On the other hand, unique counts are problematic because this could lead to re-identification. So the solution to this is to suppress low counts. So this is the same table as before, but instead of showing low counts, they are suppressed as 0. Red zeros are suppressed, black zeros are original zeros. In reality, they will be the same. So someone looking at this data would not be able to distinguish suppressed zeros from black zeros. Now, this is still not secure because the analyst or the attacker could launch a differencing attack. So in this case, the attacker could ask the query of people, males in the age range 60 to 79. This will come out 34 because this is a high count. And then the attacker could ask a query about age range 60 to 69 and get the answer 31, subtract the 2 and get the suppressed answer. So the solution to this is to perturbed counts, perturbed high counts. So more precisely, counts could be perturbed by adding noise. For utility, the noise needs to have some certain properties. It should be bounded because otherwise the answers, the noisy answers could deviate arbitrarily from the true answers. And similarly, the noise should be unbiased because if a number of queries are asked, then the accumulated noise would deviate arbitrarily from the true answer. An example of such a noise distribution is a uniform noise distribution within an interval, say plus minus 5. Now, unfortunately, this is still not enough because the attacker could still launch something called an averaging attack. And this is simple. The attacker could ask the same query multiple times. And because of the nature of the noise, the positive and negative noise values cancel out. And the true count can be retrieved by simply averaging, as the graph here shows. So the solution from Table Builder for this particular attack is to add the same amount of noise if the contributors to two queries are exactly the same. So this means if the attacker now asks the same query twice, the exact same amount of noise would be added to that query answer, and the attacker won't be able to weed out the noise by averaging. So these are the main ingredients of the Table Builder algorithm that I've just mentioned. There's some additional measures too. For instance, they hide the perturbation parameter and the suppression parameter, and they restrict the query language to make sure that the analyst could not construct sophisticated queries which would allow the analyst to circumvent the privacy mechanisms used by them. For a full set of features, you can go to this link. A crucial point that I would like to mention here is that although these privacy mechanisms are used to control or stop specific attacks, there's no proof that they withstand arbitrary attacks. And this is what we will show in our attacks. So our attacks on Table Builder are as follows. The first one retrieves the hidden perturbation parameter. The second one finds the true count, that is the noiseless or noise-free count. And we can extend this attack to find the histogram of any attribute, the true histogram of any attribute, for instance, the exact occupation distribution. A couple of things that I would like to point out. First thing is that the attacks are quite simple. And second thing is they do not require any background information about the data set. And the main ingredient used by our attack is an averaging attack on the so-called totals row or column. From the wordings of Table Builder from ABS, totals are not calculated by summing the interior values of the table. Instead, more accurate totals are provided by calculating the true total and then perturbing this value. So this total here is not obtained by adding the two noisy totals, but fresh noise is added to the actual true total. So the first attack uses the following observation. We pick one attribute with two attribute values, for instance, gender, and we ask these queries for that attribute value across different suburbs, as given here. Now, crucially, the contributors are different because these are people from different suburbs. Therefore, fresh noise is added to each of the cells and also to the totals. Now, since the number of males and females equals the total, therefore the number of noisy males and noisy females minus noisy total is only the 3 noise terms left. So our algorithm is then simple. For each suburban table, we find the 3 noisy terms, and then we keep track of the maximum, and finally we simply return the maximum divided by 3. And the results are that with greater than 95% probability, we can find the hidden perturbation parameter of ±5 in about 200 queries. And less queries are required for smaller perturbation parameters. Mitigation for this is simple. Simply release the perturbation parameter, and this follows Kirchhoff's principle that the security of the system should only be dependent on secrecy of the key used and not on the secrecy of the system itself. And this would also be useful for the analysts because they can factor in error bounds. So our second attack removes the noise, and hence we call it the noise remover. And let's assume that the attacker is interested in finding the true total of the number of males in the age range 10 to 79. Table builder will give a noisy answer. So our observation is that we divide the query into 2, hence a 2 partition, and we will ask the query, ask table builder for the 2 queries separately. If we add the result of the 2 queries, we'll get the true total plus 2 noise terms. And crucially, the 2 noise terms are independent because these are different contributors. Now, if we can find plenty of 2 partitions, we could average out the noise. And our observation is that there are plenty of 2 partitions. For instance, another 2 partition in the same table is 10 to 29 and 30 to 79. In fact, for any attribute with m values, there are 2 to the power m minus 1 minus 1 2 partitions. In our paper, we proved that each 2 partition adds independent noise, mainly because the contributors are different. With this observation, our algorithm is simple. For each of the T2 partitions, we sum the total, we divide the final by T, and we output n as the nearest integer. For the success probability of the attack, we first show an upper bound, mainly because this will be used later to show the limitations of bounded noise algorithm. Our first bounded result is based on Chebyshev's inequality, and this relates the error in finding the true answer with the variance, accumulated variance of the totals. And through this bound, we require about 802 partitions to find the perturbation parameter of ±5. Now, that was an upper bound. The exact success probability is much better. So we only need 200 queries for a 90% success rate. So we can also broaden the scope of this attack because the previous attack was only used to find the total. What if we're interested in finding the value of the, finding the count of the attribute value 70 to 79? In this case, we need a slight modification of the attack. We simply exclude this attribute value from the rest, and then we carry on the algorithm by finding 2 partitions of the age ranges 10 to 69. Once we get that answer, we subtract that true total from the true total we obtain from the attack on the total attribute. In the same way, we can carry on this attack to find the true count under any attribute value, and hence find the histogram of that attribute. So these are the results on a synthetic data set in which we chose the occupation attribute with 107 attribute values. And as we can see that with a perturbation parameter of 2, we can find all the true counts with success percentage of 100% with 200 queries per attribute value. And for lesser number of queries like 50, we also have a higher success rate. Crucially, we can also find out all the suppressed counts. Now, even though we applied this on synthetic data for obvious ethical reasons, this attack can also be applied on the actual table builder, although it requires web scraping. And we also show in our paper the same attack on the public adult data set. So what are the mitigation measures? The first one that comes to mind is to limit the number of queries. However, it's not clear what is a safe number of queries. The other one is to eliminate the total query in the sense that fresh noise should not be added to the total query. But this is, and this was exploited by both of our attacks, so this makes sense. But this is not desirable for utility because the analyst would get noisier answers for aggregated queries. For instance, if the analyst is interested in the number of males less than 50. Another recommendation, which we also suggest, is to use provably private alternatives like differential privacy, because they quantify the privacy risk as a function of the number of queries asked. Now, this last point is important because it also sheds light on the inherent limitations of bounded noise algorithms. To see this, let's recall the use of Chebyshev's inequality, which bounds the success probability with the accumulated variance. Now, to defeat our attack, this accumulated variance should be greater than any constant, but this accumulated variance in turn is dependent on 1/t times the variance of the noise. And the variance of the noise is proportional to C squared, where C is the maximum absolute perturbation. So what this means is that for accumulated variance to be a constant, the scale of the noise should be proportional to the square root of T. Incidentally, this is also the guarantee from differential privacy if we were to use a Gaussian mechanism under concentrated differential privacy. So we did communicate our attack to ABS, and they acknowledged that our attack relates to table builder, and in response to these attacks, they are making some changes. For instance, less fine-grained data available through the free version, some user-specific caps on queries, although it's not clear what is the exact cap and how is it set, and monitoring of queries to detect averaging attacks. Although, as we discuss in our paper, it's difficult to know if a set of queries are actually being used for averaging attacks or they are innocuous because they look almost the same. The ABS also has a public response to our attack. First thing, an interesting thing here is they mention that our attack is elaborate and obscure, which we disagree with, as I've shown in this presentation, that the two attacks are pretty simple. They also say that our attack is a theoretical risk, but nevertheless, they also are working with us to address it. So to conclude, we believe that it's time that data protection and disclosure control should move away from ad hoc techniques and use some more rigorous and mathematically sound techniques like differential privacy, which is done by the US Census 2020 as well. And our attacks show that if we were to use these techniques, then the noise needs to be upscaled with more queries. And this is backed by theory, like differential privacy, and a growing number of experimental evidence, as also discussed in this paper. Now, given these rigorous methods, if the utility is still undesirable, then a case should be made for sacrificing user privacy. This is the end of my talk, and please feel free to ask questions.